Palmer Science 757, Palmer Rheology, H.H. Winter Lecture 7A. Rheological material functions describe polymeric materials, and we are interested in those in well-defined flows. We can describe the polymer melts, polymer solutions in shear, in extension, by just looking at those specific material functions. Now, these functions can be used to test constitutive equations or also to model flows, like, for instance, polymer processing flows. And we looked at one example last time. I want to continue on in this example, where we looked at steady shear flow. And here in front of me, I have a kind of a summary of the conditions for steady shear flow. A material element in this type of shear flow is subjected to a shear strain gamma between T prime and T, and due to that strain history, we will generate a stress in that material element. We will generate a shear stress and 3 normal stresses. Now, the shear stress depends on the shear rate, and the coefficient is the viscosity. In steady shear flow, that's the steady shear viscosity. That's the first material parameter. And then the first normal stress difference is given by the coefficient, psi 1, multiplied with the square of the shear rate. That's the second material function. And the third material function would be the difference between normal stresses 2, 2, and 3, 3. And that also would be given by a material function, psi 2. All 3 material functions should be known to completely define the behavior in steady shear flow. With that information, we have looked at pipe flow last time. We just took the viscosity function and a momentum balance, which gave us the shear stress. So those two combined and integrated together with boundary conditions, suitable boundary conditions, gave the velocity distribution in pipe flow, and from that we can calculate average velocity, volume flow rate, or again take the derivative and get the shear rate distributed over the radius of this capillary. So the kinematics is known from this model. It's not perfect. It is a model. Remember, the viscosity function which we used is okay at high rates, but there's an error in this viscosity function at low rates of deformation, which occur in the center of the capillary. In a capillary flow experiment, we basically probe the flow. If you take the viscosity function versus shear rate, and this would, on a log scale, would be this type of function. Now, the highest shear rate occurs at the wall, if this would be gamma dot at the wall. And 0 shear rate occurs in the center of the capillary. So all those shear rates are probed in the capillary when we extrude the material through that die. So it's a whole range of from that viscosity function, we really take a whole range to describe the flow. Now, from kinematics, I would like to move to the stress. We know the flow field, we know the velocity gradient and the shear rates. Let's calculate now the stress distribution in the pipe. Remember, a transducer at the wall will give us the normal stress at the wall. That's the only information from the experiment. Now, if we take 2 of those transducer and divide the pressure difference now with the length, we can measure the pressure gradient. So from our experiment, from the measurement, we get the local pressure or the local normal stress at the wall, and we get the pressure gradient, and we would like now to know the distribution of all stress components. We would like to have the complete information for the stress. And that should come out of the modeling calculation. Let's assume that somebody measured the 3 material functions for us. So we know already the viscosity, psi 1, psi 2. So those 3 material functions in steady shear flow are assumed to be known. So that's given. And we would like now solve for the stress components. We would like to know the 9 components of the stress tensor. Well, it's not really 9 due to symmetry. The unknowns reduce to 6. The off-diagonals are equal. And we're looking at a plane stress situation. So those are 0, and we're really looking for 1, 2, 3, 4 stress components, and we would like to know all of them as a function of the radius. The x component of the momentum balance, this is the conservation of linear momentum, gives us already the shear stress. This is the off-diagonal component here. It gives us the shear stress as a function of the pressure gradient. And remember, the pressure gradient was the quantity which we got from the experiment. That can be measured. So if you know the pressure gradient in the capillary, you immediately know the shear stress distribution between 0 and the wall. R is the variable. It really goes from 0 to the wall. And the pressure gradient is negative, so the shear stress is negative. Question? Yeah, in our question is about the boundary condition. In our model, which we used to get the kinematics in the system, we assumed symmetry at the center line. That means a finite stress there, or 0 shear rate in the center. And we also assumed a non-slip condition at the wall. So the velocity at the wall is equal to 0. So those boundary conditions enter when you take momentum balance plus the material function and then start integrating. And you have to integrate twice, and that's where you enter the 2 boundary conditions to solve that flow problem. Okay, so coming back to our stress components, the shear stress is known from the experiment and from the momentum balance, and we haven't even specified any kinematics. It's independent of the flow. The R component of the momentum balance, written down as such, neglecting the inertial effects and neglecting gravity, even if the capillary goes down or in some angle, the gravitational effects are so much smaller than the viscous effects in a molten polymer that we can neglect those. If you would operate at a dilute solution, then you would certainly include the gravity in that system. Okay, so this is the R component. We rewrite this. You can decompose this term and combine 1/2 with the pressure gradient in radial direction, and the other half you combine here with this normal stress, and you basically get the gradient of pi r. This is the total stress component in radial direction, the total normal stress, and looking at the gradient in radial direction, plus 1/r times the normal stress difference, and this is really the second normal stress difference. Last time I was in my handout there was a mistake, so please note this is the second normal stress difference. And now you can integrate this function here, and you will find that the pressure difference between the wall and some local, excuse me, not the pressure difference, the difference between the radial normal stress, pi r at the wall, and some radial position is just given by the integral of this function. And this function can be expressed now in terms of our second material function, psi 2. We are assuming that we know that material function in steady shear flow, multiplied with the shear rate square. Now, note that this shear rate square comes from our solution, from the power law model. So to calculate the stress components here, we need the kinematics, which we calculated at some time earlier. It doesn't come out a priori from an experiment. Okay, we have to derive that. And if there's a mistake, in that shear rate here, because our power law model has some limitations, then we carry this mistake into our analysis in this case. Okay, so we enter this function, integrate, and then we get the pi r component at any radial position, since we know pi r at the wall. At the wall, remember, this was equal to minus the pressure which was measured with the transducer. And that's an example now where you obtain the absolute value of the normal stresses by introducing the normal stress at the wall. Okay, so that's where you get your absolute values. That's an important point in the modeling, since otherwise in constitutive equations we always deal with normal stress differences between the first and the second direction and the second and the third direction. So this is where the absolute value comes in, and we use that solution now. We know the pi r component as function of the radius from that analysis, and we add the information now from the first normal stress difference, described with this function as a functional, this coefficient times the shear rate square, and we take the second normal stress coefficient, here the second normal stress coefficient, to define the second normal stress difference, and again we get now the another component for the stress tensor. So those two are known. These we calculate with the material behavior and the known kinematics, and we obtain pi xx and pi theta theta as a function of the radius. And all 9 components are known at every point in the cross-section now as a function of this model. So with that approach, we take experimental data wherever we can obtain them, and we add the with modeling the remaining information. The velocity has been determined from the viscosity function. The velocity it just needs the viscosity, doesn't need psi 1 and psi 2, and that's very interesting information. That's actually that's really key information when you look at the relation between volume flow rate and pressure drop in processing applications. In processing applications, you can derive those relations just from the viscosity function, because you get the kinematics as a function of the pressure drop just from the viscosity. If you want to have normal stress components, the other normal stress components, you need the knowledge of the kinematics, and of course you need the material functions to describe that. So in summary, if you have the 3 material functions for steady shear flow, you can introduce those in a modeling calculation and really complete the information about the stress tensor. Here in capillary flow, you can similarly analyze slit flow, or for the homework, you will analyze the squeezing flow, the flow between 2 surfaces which are approaching each other and squishing a material flat between them, and then you apply something very similar. Okay. Let me look at another example in with steady where steady shear flow is important. The knowledge of the viscosity function, which only applies to steady shear flow and not to extensional flow, and which only really gives you the shear stress, this knowledge has been used to analyze polymer processing flows, and it has done very well. It has been very successful in predicting the relation between flow rates and pressure drops. And the question is, why is it so successful? Why can such incomplete information give reasonable predictions about flow rates and kinematics? And one reason, I believe, is the following. The flow in any flow channel reduces to steady shear flow at the wall. It reduces to shear flow in any case, presuming that there's a non-slip condition. But in the case of a steady flow situation, you're pushing a material through a channel at constant rate. In that case, the flow reduces to steady shear flow near the wall. And I want to derive that for you. Now, if that's true, if really the flow reduces to steady shear flow near the wall, then you're doing all right with the 3 viscometric functions when describing the stress in a material element near the wall. Okay, so near the wall, those viscometric functions are applicable. They are suitable to describe the rheology. And near the wall is the position of highest stresses. So when you talk about the pressure drop and the viscous dissipation in polymer processing flows, a lot of dissipation occurs near the wall. And if you, for instance, lubricate the wall, then you change the stress levels, and you change your whole kinematics drastically. Or in other words, if you are okay in your analysis, in your modeling of the flow near the wall, then you are far along in modeling of polymer processing. Okay? So let's look at this theorem here. It says that for any cavity where we push some fluid here, say from left to right here, we can look at a material element at the wall, and at the wall the flow reduces to shear flow, provided that there's a no slip condition. That's necessary. For that purpose, we would expand the velocity in a Taylor series. Like here we say the velocity at some function x is equal to the velocity at position 0, that for instance might be a point at the wall, plus the gradient multiplied with the distance from that point, and plus some curvature and you can take some higher order terms, but it's really not necessary since we are looking just at the limiting conditions near the wall. For our purposes, we choose a coordinate system where the 1,3 plane is tangent to the wall, and 2 would sticking out normal. Yeah? And later on, we even can change that. We can specify this further, and we could say the flow direction. Say if we are moving away from the wall a little bit outside, we notice some flow. At the wall, velocity would be 0, but at some small distance, delta x2, there will be some flow, and we would identify a flow direction and use that as our one direction coordinate system. But that's really not essential at that point. Just we will come back to it a little later. So near the wall, first let's stay at the wall. We would assume no slip condition. The velocity at the wall is 0, and the gradient in tangent direction, so in x1 or x3 direction, this is the tangent along the wall, would maintain the same value, so the gradient is equal to 0 for our velocity field. And keeping this in mind, we could now look at a material element near the wall, very close to that, and in that material element, we also would say that the gradient tangent to the wall, like in x1 direction or x3 direction, is very, very small compared to any gradient normal to the wall in x2 direction. So somehow when we move away from the wall, there is a sudden increase in velocity. It goes from 0 to some finite value. So this gradient is much larger than this. In the equation for conservation of mass, where we have u1 gradient in one direction, u2 gradient in two direction, u3 in three direction, those two gradients will be very, very small, will be really close to 0 near the surface, and we can say that the gradient of u2 with respect to x2 at the wall is about 0 from that derivation. Now, all those gradients enter in the definition of the local rate of strain tensor, and when you put in all components, you will see that the only non-zero components are the gradient of u1, normal to the surface in x2 direction, and the gradient of u3, normal to the surface in x2 direction. Those are the finite contributions in that tensor in the limit of the wall position. Now, if we really choose u1 being the coordinate in flow direction, then there's no flow in three direction, and this component really drops out. We are free to choose our shear flow coordinate system whichever way we would like to. And then you can see that the rate of deformation tensor reduces to shear flow, and if the velocity is independent of time, u1 is independent of time, then the shear rate is independent of time, and you have steady shear flow. And I think that's quite amazing. For a while I took complicated constitutive equations and modeled flows, and whenever I got close to the wall, everything reduced to shear flow. And this is why. You can see that. This holds for any type of constitutive modeling. And it's good information to know. Bruce Caswell derived something like this for specific constitutive equations many years ago, but it's really independent of constitutive equations. This much about material functions in shear flow. We looked at dynamic shear, we looked at steady shear. Let's go to the other interesting kinematics, extensional flow. And let's look at the material functions in extensional flow. For that, just as a reminder, we have a flow for which we can choose a suitable coordinate system which will remain orthonormal at all times. It doesn't have to be tangent to our streamlines. It's just given by the specific kinematics, and we have to find out what coordinate system that is. If we would describe extensional flow in another coordinate system, everything would be a little more complicated. But since we are free to choose without losing any generality, we will pick that coordinate system. We have the stress response now in form of 3 stress components. And again, 2 material functions are of interest. The first material function is the difference between tau 11 and tau 22, and the second material function is the difference between tau 22 and tau 33. Now, this material functions can be measured in extensional flow. And that goes something like this. You would take a little element, say a little fiber, and subject that to a stretching force. And this force, say, is equal to a normal stress in one direction times the instantaneous area of the fiber, instantaneous area of that cross-section. Now, in a real experiment, and let's postpone the discussion of the experiment of how to do that. In a real experiment, your transducer would see the total force, and if this stress response is constant, the force decreases as the fiber gets thinner and thinner, and that will be a limitation. It's a very hard experiment to do. Okay, so this is the force, and sideways, there will be a normal stress on that surface, and this normal stress is equal to minus the ambient pressure on this side. So it's basically 0 under most conditions if we have a large stress acting on the system. We also have to specify the kinematics. We would want to say that L is the length of this fiber, and the whole experiment is called uniaxial extension. In an experiment in which we would like to measure the material function, we would prescribe the extension rate as a function of time. Now, the system would be at rest for a long time, and then at time t equals 0, we would start stretching this fiber at a constant extension rate. And the extension rate is defined as 1 over the instantaneous length times the length change with time, right? You know this definition. So this is given. This is the part of the experiment which we are prescribing, and we would like to measure now the response, the stress response. Now, what type of response would we be looking for? We would look for the material function, and this material function, remember, is given as pi 11 minus pi 22. This would be the stress response, which this is the first normal stress difference. The stress tensor is diagonal, so it has only 2 independent components, independent material functions. The second material function, let's complete that in a moment. The second material function would be pi 22 minus pi 33, and that's equal to 0 due to symmetry. Those two stress components are equal. So this is the only material function to look at. And let's divide this already with the rate of extension, which we would say is constant. Here, this is our constant rate which we use for that experiment. Now, data look something like this. The stress or the type of viscosity as specified here, it is a viscosity. It's stress divided by rate of strain. This viscosity increases as a function of time. This is the stress response. And after some time, interesting enough, it turns up. It starts to grow. And a quantitative equation, for instance, large rubber-like liquid is able to model this type of behaviors. Even Lodge was predicting that before data were available in uniaxial extension. So this is the stress response, and this function here is actually 3 times the startup viscosity in shear flow. When you take a material element at rest, and then you start shear flow at constant rate, then the stress grows as a function of time. And if you divide that, you have a viscosity as a function of time for that material element. Now, in the limit of low rates of deformation, where you don't have the overshoot, then you measure this function, and 3 times that function is now given in extensional flow. And the factor 3 comes simply from the geometry. So before showing some data, let me derive this factor 3 for you by looking at a Newtonian liquid in uniaxial extension. Now, this Newtonian liquid would be given by, say, a stress tensor equal to a viscosity times 2 times the rate of deformation tensor. And in components now, for uniaxial extension, we would have tau 11, tau 22, tau 33. We only have the diagonal terms covered because of the specific coordinate system we are allowed to use in uniaxial extension. And this is now equal to the viscosity and 2 times the rate of deformation tensor. In uniaxial extension would be twice epsilon dot. Now this is our constant rate here, or epsilon dot 0, and this is epsilon dot minus epsilon dot minus epsilon dot, and we have zeros in all other positions. And now you can see that tau 11 minus tau 22 is equal to mu times 2 epsilon dot plus another epsilon dot is equal to 3 epsilon dot. So for the Newtonian case, you have, I'm running out of space here. For the Newtonian case, you have tau 11 minus tau 22 is equal to 3 times the viscosity times epsilon dot. And this is sometimes called the Troughton viscosity in extensional flow. But it is no new property. It is the same property as we discover in shear. The only assumption in this derivation was that we have constant density. Yeah, we haven't considered any volume changes, and that's a very good assumption in this case. So in the Newtonian case, we have 3 times the shear viscosity, something discovered by Troughton 1907 or so a long, long time ago. And then it got forgotten, was rediscovered many years later as some magic miracle, but there's no, it is just the geometric relation coming out of this. And we find the same behavior for polymeric liquids in uniaxial extension. The first person who could measure these functions was Meissner at the BASF. And here is his famous data set. It's somewhat too big for, if you reduce that little Okay, so we are looking at the material function, right? The normal stress difference divided by the weight. This would be viscosity as a function of time. This curve is basically the linear viscoelastic limit. At some time, there's an upturn to somehow the material is getting stiffer. It looks like a flow-induced crystallization. So the material is stiffening, and this upturn occurs earlier at higher rates of deformation. Somehow the growth cannot go ad infinitum. There has to be some leveling off, and the question is really, is there a steady shear, is there a steady extensional viscosity? You know, those are transient viscosities. Does it really level off and then stay constant? And it's hard to measure because of exactly this fact I discussed before, that the cross-section gets smaller and smaller as you get to larger and larger deformations. And then your transducer value is biased by noise. Also, the measurement might be biased by surface effects. The ratio of surface to volume increases drastically when your fiber gets very thin. And then you might not measure bulk properties by themselves, but you might measure a combination of bulk property and surface property. So it's a question of long disputes. What will happen at high values of deformation at very long times in extensional flow? While in shear flow, it's settled. There are lots of data, and we know that we can use steady shear behavior, and everything is fine. The temperature effects are also very interesting. The behavior in shear and extension depends very much on temperature. And we saw that the shifting of the viscosity curves resulted in a master curve. They all could be shifted into a single viscosity curve. And similar temperature effects can be found with various material functions. I listed not only the viscosity here, but listed the relaxation modulus as one material function. Remember, we had that initially when deforming a material and looking at the relaxation behavior. So we would have a time-dependent modulus measured at two temperatures, at temperature T0 and a new temperature T. Also, then viscosity we would measure as a function of shear rate at two temperatures, temperature T0 and then at another temperature T. And then you might characterize relaxation time. That could be the break-off time in the viscosity curve. You know, the transition from the zero shear viscosity to the power law. That decision indicates a characteristic time. This characteristic time is the inverse of the shear rate at this level. And you could now describe the temperature dependence of this time in some fashion. Now, what are the relations between the two? A good source for looking at those material functions would be Ferry's book on linear viscoelasticity. So the relation between the modulus at the new temperature T and the modulus at the other temperature T0 is given by a shift. Somehow our time of observation has to be changing because of the temperature effect. So our new time here would be T divided by AT. And then also density effects are coming in. We have the density at some absolute temperature T multiplied with T divided by the density at reference temperature T0 multiplied with T0. Now, this fun factor, sometimes called BT, is about 1. It's about unity. But our time scales of relaxation are certainly changed when going to higher temperatures, and we have to account for that. I brought an example of this type of function. Here is the modulus. Here, this is the relaxation modulus measured by Nielsen in '62. Now, his time of observation was very limited. His rheometer only went over about 2 or 3 decades in time. And he measured the modulus at a wide range of temperatures. The material is a polyisobutylene. Now, these curves were shifted by introducing the time scale T over AT, and then the curves resulted in a modulus curve, which has the glassy behavior here, glass transition, rubbery plateau, and flow behavior at very long times. Note that the experimental window has been increased drastically by this time temperature superposition. Of course, Nielsen picked a nice example which had a high temperature dependence of those properties. The shift factor itself is plotted here as a function of temperature. Now, when you look at those shift factors, AT, then you find the value here, value 1, to give you the reference temperature. The reference temperature of all the data is 25 degrees C. Because their AT would be equal to 1, and then your time scale is the real time scale which your observation is occurring. Okay, so this is the relation for the modulus. Similar relations could be derived for the viscosity functions. The viscosity at shear rate gamma dot and new temperature T is equal to rho T over rho 0 T0 times the viscosity at shear rate. And now the shear rate has to be shifted because the relaxation processes are sped up. They are increased at higher temperatures, so we have to account for that by multiplying the shear rate with AT, and this would be then the function, viscosity function measured at the reference temperature level T0. And for the relaxation time, we have a simpler relation. The relaxation time at temperature T is equal to the relaxation time at the reference temperature T0 multiplied with the shift factor AT. Yes?
For the steady shear viscosity, you have beta is a function of AT on this sheet.
Oh, yes. Yes, right. Thank you. Yes, and this is multiplied with AT. Yes, right. Yes. This is associated with the, here, if we have our viscosity functions, those are shifted under 45 degrees, and our axis would be gamma dot AT and would be eta over AT. And remember, we are talking about a log-log representation. So the question was why we need this AT for the viscosity function. Later on, when we discuss linear viscoelasticity, I will come back to these shift factors. In the moment, I could say that this is an experimental observation, and from that observation, we are finding this relation. Okay? And we will use that. Interesting is that all those functions are, these AT functions are the same, independent whether we look at the relaxation modulus or whether we look at the viscosity or whether we look at the relaxation time lambda. Now, there are some empirical relations describing these shift factors. Empirical relations, and the most famous one is the so-called Arrhenius relation, which says that AT between two temperatures, T and T0, is given as an exponential function So it's e to the exponent e over r. E is an activation energy. R is the gas constant. So the whole thing has dimension of a temperature in Kelvin multiplied with 1 over T minus 1 over T0. Okay. In this relation holds for low molecular weight liquids or for polymeric liquids at very high temperatures, much above the glass transition temperature. It hardly holds for any data. When you take molten polymers at different temperatures and shift their material functions, you hardly find the Arrhenius relation. It's somewhat more complicated. So the next the next type of relation is proposed by Williams, Landau, and Ferry. It's the famous WLF equation, which comes up in so many relations. And this is a function which doesn't have the E as a basis, but has 10 as a basis. So it's 10, maybe because they plotted their data on log papers, with decimal system. So it's 10 to the minus C1 times T minus TWLF, let's call it. Yeah, it's a material parameter, divided by some second constant, C2, plus T minus TWLF. Okay? So that's a relation which describes a large range of data, large range of observation at various temperatures. So, and it also holds near TG. We are still talking about the flow behavior, so we are above the glass transition temperature, but near TG, the WLF equation holds and describes the data very nicely. I brought some values here for the functions, for the parameters in this function. For instance, in the WLF equation, the constants C1, C2 are pretty much constant for a large variety of polymer melts. So we could call them universal constants. Well, that was the proposal of WLF. And a parameter here, this WLF time, is close to the glass transition time. This temperature, WLF temperature, is close to the glass transition temperature of the system. Okay, so those would be the material parameters. Now, it turns out that this complicated equation is equal to an equation which had been proposed much earlier by Vogel for some other materials. He didn't realize that. But this shift factor in this form, e to the constant divided by t minus the Vogel temperature, is exactly equal to that formulation up here. And you either checked it yourself and believe me, or you don't. So I brought an example. I wanted to show you that those two are really equivalent, that it doesn't matter. It is well known that they are equivalent, and people are using the Vogel equation now preferred to the WLF because it's such a more simple format. So let's go through an exercise of temperature shifting here. We would like to shift a relaxation time from a temperature level T0 to a new temperature T, and given, say, our data of lambda at some reference temperature, not at T and not at T0, but at some reference level, and we would like to shift from there. Now, the relation which I had out here on the blackboard for the shifting is repeated here. So lambda at temperature T divided by the shift factor between T and this reference level is equal to lambda at some temperature T0 divided by AT 0 also with respect to this reference level. Now, the ratio of those two, described with the Vogel equation, can be expressed just in exponential function. The two exponents are subtracted from each other. We are recombining this, and we find now that T minus T0 appears up here, and T and T0 here. T and T0 appear down there. So let's keep this solution in mind, and then we do the same process here, go through the same exercise with the WF equation. The two lambdas, ratio of the lambdas, are given by the ratio of the shift factors. We calculate this with 10 as a base now, and we combine those two exponents here, and when you rearrange all this, you'll find the solution here. And now let's compare. I brought some pen here. So this term here appears up there. Okay, then the temperature down here occurs down here, and also T0 occurs down here. So if C2 minus TWLF is equal to the Vogel temperature, right? This would be this would be one of the constants here. This would be equal to this combined, and then the other constant here, A, is given with C1 and C2, and that's it. I hope I convinced you that this is that both forms are really equivalent. Now, all the data I showed you about the temperature depends, all the material functions are much above the glass transition temperature. I haven't even mentioned the glass transition temperature, but if you would say that a material below Tg is in some non-equilibrium structure, somehow temperature change affects the structure in the material, and at high temperature the structure can equilibrate very rapidly, and we would look at equilibrium structures at all times, at least during steady state experiments. Now, if you go below Tg, then the structure cannot go to its equilibrium formation. The molecules are out of equilibrium, and this will give rise to some new properties, and it's much more complicated. In fact, the temperature history is very important in this case, because you might be closer or further away from the equilibrium, and depending on that, you get different properties and you get different experimental results. This is all I wanted to discuss about material functions. In a moment, we will switch tapes now. In a moment, I will go to the next subject. Science 757, Polymer Rheology, H.H. Winter, Lecture 7B. Okay. Yeah, for measuring the material functions, we need some instruments. And I haven't even mentioned that. I just assumed that we are able to measure the stress and measure rates of deformations. So those instruments are called rheometers. Rheometer is an instrument which produces some well-defined kinematics, and allows to measure stress and strain as a function of time. Now, those rheometers have to be built differently for shear flow. So I will first talk about shear rheometers here in the first part, and secondly about extensional rheometers. The shear rheometers are basically divided into pressure-driven systems, so-called capillary rheometers, and then rotational rheometers, where the relative motion of two surfaces introduces strain into the material, and we would measure the resulting stress. So let's start out with capillary rheometers. Oh, here I forgot I wanted to discuss some general terms before going to capillary rheometers. What would you do as a designer of a rheometer? What's desirable to have? Well, first of all, the rheometer should give well-defined flow geometries in shear and extension. And maybe in the future we have to think of a rheometer which gives a mixture of shear and extension to test some constitutive equations. And very little has been done. It's very hard to make progress in this respect. So we just take shear flow and extensional flows. There are instruments which do not produce well-defined flows or well-defined kinematics, and they're still used as a type of rheometer. Those are called indexer. For instance, the melt indexer is an instrument where a polymer is pushed through a die. It's accelerated, so the material element is stretched in the entrance of the die, and then there are all kinds of phenomena which are related to the pressure drop and the flow rate, which is measured in the melt indexer. So the flow is not defined, but you still can distinguish between a material which flows easily and a material which is very hard to push through a die. So in industry, the melt indexer is very popular as a simple tool to characterize processing behavior. But here we would like to look at well-defined kinematics. The main functions of the rheometer would be the measurement of stress and strain. After having generated the right strains as a function of time, we would also measure that. The temperature should be controlled, since the properties depend very much on temperature. And somehow the sample loading and unloading is important. It's very hard for melts, and for solutions it's of course fairly easy. Now, the mode of generation could be steady, like in capillary rheometers, or if you want to look at transients, we have to be able to produce transient kinematics in that system, and we have to learn how to do that. Deformations might be very small or large, depending on whether we look at linear viscoelasticity or large strain behavior. And different rates could be applied for polymer processing applications. The rates are very high, so we would like, if we want to simulate the behavior near to polymer processing conditions, we would produce high rates. And then some options. You know, if you would build a rheometer, you want to do something which is unusual, which can do more than other rheometers. So you have to put in some special things. The environmental condition here that oxygen is excluded, that's standard. We just use protective gas to cover the free surface in a rheometer. But a rheometer for high pressure is basically not available. We should maybe do something about this. Then windows on the rheometer might help optical studies doing birefringence, dichroism, fluorescence. We, for instance, look at fluorescence measurements in polymer blends, and I will talk about this when we reach the polymer blend area. So that's interesting to combine optical techniques with the conventional rheometry. Now we combine Raman measurements, for instance, in the rheometer with shear information. And then the sample should be small, because the chemist will make some fantastic new polymers, some exploratory research, but he only will give us very small samples. So we should build rheometers to accommodate the chemist to be able to team up with them. And then the sample should be recoverable. So after having done this experiment, it should be able to take it out again. So this is connected really with the problem of molding. We not only want to load it and then unload it in some fashion, we would like to unload it so that the sample is intact, and we can look at the morphology which we introduced into the sample by some fancy type of flow. We can We can use floats, for instance, to push the material away from equilibrium, produce some interesting morphologies, maybe some chain extension, and quench the sample with that interesting morphology. And flow will give us properties which are better than the equilibrium properties which we would conventionally get from some self-assembly when looking at equilibrium behavior. So that's a very interesting field in rheology. Yes? Which one? Oh, dichroism. It's an absorption phenomenon which basically looks at the absorption bands of specific parts of the molecules. So you can have, and it also depends on the local alignment of the molecules. So by shining light in your sample at different directions and looking at the absorption in parallel or normal to your molecule, you get information about the local molecular orientation. Oh gosh, yeah, I don't know. It really depends on your molecule. You use monochromatic light, which is in the right absorption band of your molecule. So it depends on the absorption of your system. Okay, now let's go to capillary rheometry, or let's go to shear rheometry in general. In shear flow, as we know by now, we would like to generate this type of kinematics and would like to measure material functions, the three material functions. And in the capillary rheometer, the shear rate is constant. We would measure those three functions at constant rate of deformation. That would be the objective of capillary rheometry. In a rotational rheometer, where we look at transient, we would look at the same material functions, but time dependent, as the transient behavior of those material functions. So here we look at steady shear flow, and I brought an old drawing. It even has some old German writing on it. It's an instrument we had in the lab. Becky, if you change the scale a little bit, I have maybe get an overview here. Yeah. The sample is in yellow here. The sample is contained in a cylindrical cavity, and this cavity is heated. There's temperature control around here. A piston displaces the sample. It's really pushing the sample down, and on the bottom you can see that this reservoir is connected to a die, to a channel of very small diameter. This might be a capillary of circular cross-section or might be a narrow slit. The volume flow rate is given by the velocity of this piston times the area of that piston, provided that we reach steady state. When you start up, you first compress this polymer somewhat, but as soon as you reach steady state, this piston velocity gives you the volume flow rate, provided that there's no leak, so we need a good seal up here. Secondly, the second quantity to measure would be the pressure in this capillary, and in this case we would mount pressure transducers, two transducers, along the capillary and measure delta P divided by delta L, and that gives us the local pressure gradient, and that's a second property the second quantity which we needed comes out as a result from this experiment. The die itself, here I show you a picture of this die here. Actually, I designed it myself and then showed it to Göttfert, producer of capillary rheometers. He didn't want to look at it, but then when he saw it in the lab, he said, yeah, I like it. And he produced it, and he sold many of those, and just by seeing that. But I should mention that it wasn't my idea. The idea was published earlier by Janusz Kriegel in the beginning of the 70s. So they pushed this the slit geometry. I added here those pressure transducers here with small holes. The transducer is sitting back, See, the transducer itself is too big to be mounted on this space-sensitive slit. So we have just a small hole here. This is a blow-up version, a small hole. This is the flow channel. And the pressure in this cavity here, which is connected to the membrane of the transducer, is equal to the pressure out here in the channel. Now, there's some error involved in measuring the pressure this way, but since the error occurs twice at two transducers, when we subtract the two values, the error cancels, and we get a very good pressure reading, and it's very successful. Temperature control is needed also. Downstream, the capillary is only this long. Downstream from here, we have some more metal to just protect the temperature field in the die. To have isothermal conditions, we need zero temperature gradient in this direction. That's why we are producing it this way. So it has various advantages to take this experiment in slit flow. The classical experiments actually haven't been done on the slit. I just mentioned Janishits's paper on Janishits-Krieger's paper in the 70s, where he published slit data. Now, here, could you even change the scale even bigger? Yes, good, just for this one slide. The popular way of measuring viscosities goes like this. There are capillaries attached to the reservoir, and the pressure drop in the capillary is of interest. Now, the flow needs some time to develop, but after that development time, the pressure gradient is constant. The flow we would call a steady shear flow, and we would like to know the gradient in this region. But in effect, we measure maybe the pressure upstream here, or we measure the force in our drive system. We are far from knowing the pressure gradient in the capillary. So we have one pressure value for a capillary of a certain length. This is our first data point. And now comes the suggestion of Bagley. It's the so-called Bagley correction. He says, let's repeat this experiment at exactly the same condition. Just perfectly the same rate, same temperature, everything the same, except by using a capillary which is by delta L extended, by delta L longer. And in this experiment, we would encounter a higher pressure, right? This added resistance gives rise to a higher pressure. And this delta P is associated with delta L with the length change. And now comes a key point. If the flow in the capillary has reached steady state, then the extension of this capillary will only extend the steady shear flow region of this capillary. It will not change the end effects at the outlet. It will not change any entrance effects of this capillary. It will just make the steady shear flow region longer. Therefore, when dividing delta P with delta L, we have measured the pressure gradient in the steady flow region, steady shear flow region of the capillary. And that's what we need for calculating the shear stress. It's quite tricky, right? Now, in the slit, we can measure directly. So we use one instrument to measure the pressure drop and divide it by the length and get the gradient. That's for the slit, available immediately. And for the capillary, you have to take off one capillary and put on a new capillary. 2 capillaries are not good enough because of experimental error, so you want to do it with 3 or 4, and then you would draw this line here through the data points, and it's quite involved. So by using the slit, you save a lot of work. You get a lot of data in very few experiments. So what's the status of our experiment now? We measured with the rheometer flow rate, and we measure the pressure gradient. In the slit, we measure directly. In the capillary, we use Bagley correction to get the pressure gradient. The volume flow rate will be used to determine the shear rate, and the pressure gradient will be used to calculate the shear stress. And as you know from the momentum balance, we went through the detail of the stress today. You know already that the shear stress is related to the pressure gradient by a linear function. It's just R over 2 times the pressure gradient. So if we know the pressure gradient, we know the shear stress in the entire cross-section of the capillary. But we don't know the shear rate. We are stuck so far. And that needs some more involvement to find the shear rate. Now for finding the shear rate, we have to model the flow, which we did. We will assume that the flow is fully developed. It's a steady shear flow we are looking at. The flow is fully developed kinematically. There's some acceleration involved in the entrance of the capillary. Will be fully developed rheologically. See, the material element has to be subjected for some time be subjected to shear flow for some time until reaching steady shear condition. And at the wall, there should be no slip, should be isothermal, and steady flow condition. We wouldn't pulse our flow rate, for instance, would be constant flow rate. And then the density changes should be small. If there are any deviations, the analysis will be much more complicated. Let's look at the case of the developing flow. The material moves from the reservoir into the capillary, and pretty soon the velocity field will be established, and then material element move along a streamline here, but they still have to accumulate a lot of strain. Remember, after about a shear strain of 20, fully developed flow is reached. Now let me draw here. Yeah, this is a cross section here, and those are lines of constant shear strain. And let me specify what I'm doing here. This is the axis down the capillary, and at position 0.5, this would be between the axis and the wall, the material element just halfway. That element has to go down the channel this far to reach a shear strain of 20. This is here, gamma equal 20, this line associated with gamma equal 20. Now, a material element near the wall, say at 75% near the wall, has to go only this far down the channel to reach steady state. And a material element at 25% has to go down this far to reach steady state. So it has to go 45 radii down the capillary to reach 20 shear units. It needs a long, long time to reach steady state, steady shear flow conditions. In birefringence experiments, you would probe the sample over the whole cross-section, and you would see that in the center line, it needs a long, long time to introduce sufficient strain and to achieve steady shear flow conditions. Steady conditions also would be reached with time if in the linear viscoelastic range, if the deformation is really very small, or rate of deformation is very small. But that time is so much longer for most polymers than the residence time in the capillary. It will rush here through the capillary before it can equilibrate. We only can hope to reach steady shear conditions by imposing a large shear strain on the material. So note, only say up to here, at say 15, only this part of our capillary, of this part of the material in the capillary has reached steady shear flow. The other part is still developing. Now, it turns out that the outer part in the capillary determines the pressure drop flow rate relation. So our measurement is okay because we are reaching steady shear flow in this outer region. And that is associated with this example that for any channel at the wall, you reach steady shear flow under those conditions. You immediately reach steady shear flow at the wall when the material enters the capillary. But when you have a finite layer thickness, you need a finite length to reach steady shear flow. Okay? So that is what we call the rheological development in the stress when sitting on a material element which is moving through the capillary. And we assume that the stress is fully developed. Oh, I only have a minute and a half. Let me see how far I can get with the so-called Weissenberg-Rabinowitz correction. I'm still trying to get the definition. I still want to calculate the shear rate at the wall for given volume flow rate. So given volume flow rate, given pressure gradient in the capillary, and from that pressure gradient, we know now that the shear stress at the wall is equal to this pressure gradient times R over 2. And we also know that the stress increases radially. It's just a linear function of the radius. The observation in our experiment is the following. The volume flow rate measured for different pressure gradients or different shear stresses. Now, the volume flow rate divided by pi r cubed. If we plot our function like this, which would be like the average velocity divided by the radius. It's like an average shear rate. It's called an apparent shear rate, really, of the material in the capillary. So if we plot this apparent shear rate versus the shear stress, there is one curve for all our experiments at any radius. If we repeat our experiments with capillaries of different radii, we only get a single curve describing this behavior. And I have to show to you from the model why we are obtaining one curve. Now, I will derive this next time because I'm really running out of time. So next time we will come back to this. We will come back to the Rheometry correction to calculate the shear rate at the wall in the capillary. We already know the shear stress at the wall, so having shear stress in shear rate, we can determine the viscosity from our measured values in the capillary rheometer. We also will discuss a second way of determining the shear rate. There's an even more elegant way, let's say a simpler way of determining the shear rate in capillary rheometers, which gives you the value instantaneously in a very simple fashion. So I will go through this. And then we will discuss different possibilities you have with a capillary rheometer. We will go through the details. So next time we will continue with the rheometers.